All right, 10.3, we're going to look at parametric equations and calculus. And so we're going to actually be using some of the things that you were doing on your gateways, which is why we were practicing on that too, is because we were going to get to them here. All right, so some reminders. In calculus, that is Calc 1, in Calc 1 we learned how to calculate the slope of y equal f of x. We'd like to do the same for plane curves. Right, what we did for functions, we'd like to be able to do for plane curves. So theorem 10.7 talks about the first component of that, and that is about derivatives. So parametric, this is the parametric form of the derivative. All right, if a smooth curve C is given by the equations, x equals f of t and y equals g of t, then the slope of C at xy is dy dx equals y prime of t divided by x prime of t. Or if you prefer, you can write them as dy dt over dx dt. And your book uses both notations, so be prepared for that. This other piece that I'm going to put in here, I tried to decide where it makes the most sense to put it. I'm going to put it in here. It's not part of theorem 10.7, but it's going to come right on the tail ends of it anyway. So we're going to talk about the second derivative here. If you find the second derivative, remember that's d2y dx2, right? The second derivative of y with respect to x twice. It's actually creating a chain rule because we have t that's embedded, or these functions f of x and, f of t and g of t that are embedded inside of these other functions, right, as we're finding derivatives. So what ends up happening is we're finding the derivative of x of dy dx. But when we do that, it actually creates a chain rule situation. So we have the derivative with respect to t of dy dx, because remember dy dx is in terms of t, and it's divided by dx dt. So it's not as simple as just take the second derivative of the numerator and the second derivative of the denominator, much like the quotient rule is not just take the second derivative of the numerator, take the second derivative of the denominator, right, when you take derivatives initially anyway. So we'll come back to this definition, and it's not the first example, but it's the second one, and we'll use this idea for our second derivative in a moment. Okay, so our first one, straightforward, very nice and clean one. We're just going to find the derivative. So we have find dy dx, and we're finding dy dx of the parametric equations x equals t squared, y equals 7 minus 6t. Can we find a piecewise? So this first derivative, the derivative of x, or the derivative of t squared, is 2t. And the derivative of y, or 7 minus 6t, is negative 6. And if we want to find dy dx, we do, and I'll flip back over here to see it, although I'm sure you have in your mind already, the derivative of y divided by the derivative of x. Okay? So the derivative of y here is negative 6, and the derivative of x is 2t, and that, of course, simplifies to negative 3 over t. So first derivatives are really clean and straightforward. They're just putting a quotient together of two separate derivatives that you already know how to find anyway. Okay? The next one has us find the first derivative and the second derivative, and it is messier because of that second derivative notation. So our second example, we're going to find dy dx and d2y dx2. There's one more piece of this. And the slope and concavity at the given parameter. Okay, so we have x is cosine of 2t, y is sine of 4t, and the given parameter is pi fourths. T is pi over 4. So half of this is just like the last problem, just finding the derivatives, putting them on top of each other. I shouldn't say half, maybe a third. And then we're going to evaluate it at pi fourths, okay? So let's start with that part. That's definitely the most straightforward part. I'm going to do it underneath here because I'll have more space for the other half of it, which will be much longer. So what is the derivative of x? That is the derivative of cosine 2t.
Negative 2 sine 2t.
Good. Negative 2 sine 2t. How about the derivative of y? 4 cosine 4t. And if I want to do dy dx, I'm going to change this up just a little bit. Dy dx will take 4 cosine of 4t divided by negative 2 sine of 2t. Because the angles don't match, there's no combining them with like cotangent or something. You can't do that. But we can at least simplify the 2 and the 4 at the beginning. So I have, I'll just put the negative on top, negative 2 cosine of 4t over sine. You know what? Let me just leave the negative down here. Well, it's fine. It's fine. Sine 2t. Good. Okay, so this is one of the 3 parts of the directions, right? Or 4, if you will. And I'm supposed to evaluate this at pi over 4. So we're going to evaluate this at pi over 4. And because this is going to be such nice values, you probably know them. If you don't know them, you want to just use your calculator to find them very quickly. You can do that as well. So we're going to evaluate this at pi over 4. All right. So I paused briefly, and everybody probably already has all their answer now, right?
Yes.
Yes. What'd you get, Jubal?
I got 2 square root of 2.
You got 2 square root of 2. That's not what I have written down. You got 2?
I just got 2.
Okay, 2 is what I think I have too. So Annika, you're the first one who said it. So tell me what you got for the top. There's a 2, negative 2 out in front.
Well, cosine of 4 times pi over 4 is negative 1 times negative 2.
Yeah. And then the denominator is 1. Yeah, so because we have the 4 inside and the 2 inside of the cosine and the sine respectively, we end up with some nice whole values that keep us out of those radical 2 kind of angle measurements. Did you find your error, Jubal?
Yeah.
Okay, perfect. All right, so I'm sorry I didn't finish this out. Like you just said, this is a 2. So the slope at that particular value is 2. Okay, everybody good with that one? Fabulous. Okay, the other one, you ready for that one? Okay. All right, we're going to do the second derivative of y with respect to x twice. And I'm going to jot down what it said on the previous screen, what I wrote. That's the d dt of dy dx and it's divided by x prime of t, or dx dt, if you prefer. I'm just going to shorten it. Okay, is that okay? Did I rewrite it right? Still good? Okay. So I know the first, I know the embedded piece, and I know the piece in the denominator. So I need to do d dt of this piece over here that I had right there. So negative 2 cosine of 4t over sine of 2t. And all of that is divided by the derivative of x, which was negative 2 sine 2t. Okay, is that all right? So what do we have to do now with that d dt in front of that? What's it telling me to do?
Take the derivative of
Which is going to involve what?
quotient.
Quotient rule, yeah. I need to take the derivative of what's in parentheses where I am at the moment, which is going to involve the quotient rule. It's kind of messy. Some of the pieces are going to cancel out nicely, and the ones that don't, we're evaluating this anyway, right, too? So eventually things are going to collapse, much like they did on the last one, with a lot of ones going on and some zeros in there as well. So, yeah, so we're going to do a quotient rule. So we're going to do the denominator times the derivative of the numerator. So what's the derivative of negative 2 cosine 4t?
Negative.
Negative or positive?
Positive.
Positive. Positive 8 sine of 4t. So it's the first half of the numerator minus. Now I need the numerator. Sorry, I've got notes inside where I've simplified as I've went. So the numerator, which was negative 2, so negative 2 is going to make it a positive 2 cosine of 4t times the derivative of the denominator. So what's the derivative of sine of 2t? Yep, negative 2 cosine. I think it's positive. Should be positive? 2 cosine 2t? Is that okay? The derivative of sine is cosine? Yeah, okay. And all of that's over the denominator squared. And the denominator squared is sine of 2t squared. And right now, this denominator right here should be underneath the entire thing. But that's the same thing as putting it in the denominator that already exists. So I'm going to go ahead and just put it in the denominator that already exists so that I don't end up having double denominators going on. Are you good with that? So I have the negative 2 sine of 2t down here, which is actually very nice because what do you notice about that denominator now? It's just sine of 2t cubed, right? There's 2 of them here, and then there's another one there. There's still a negative 2 in front of it, but aside from that, I have 3 of them. So the denominator is negative 2 sine cubed of 2t. Holy moly on the top. Let's just see what we have. All right, so that looks like 8 sine 2t, sine 4t. You can't just go sine 8t or sine 6t. It doesn't do that, right? This is some, there's some trig identities that you could use to simplify that if you wished. That's not our goal right now, but there are. And then on the other piece, I have plus 4, and then I have cosine of 2t, cosine of 4t. Okay, what do you think? Nobody wants to say yuck. Really? It kind of looks like yuck. There's really not, without some trig simplification that's, again, further along the lines of trig than we're going to go, there's nothing else we can do. We can't cancel anything out nicely. We can cancel out the 2's, I guess. We could do that. I take that back. So this one, and this one, we could reduce all those if you wish. So we could have a 4 here, and a 2 here, and a 1 here. So we might want to do that. But that's it. There's really nothing else. Let me see if I can move this to the other screen so that we have the ability to keep working. All right, so I have, for my derivative, my d2y dx2, I have 4 sine 2t sine 4t plus 2 cosine 2t cosine 4t over negative sine cubed 2t. Okay, that's our second derivative. It wants us to find the concavity at the point pi halves, or pi fourths, right? So now we're going to do the same thing we did with the derivative. We're going to evaluate this at pi over 4. So evaluating each piece, so we have 4. This will be the sine of, I didn't write it in on the last one, but it's kind of a messy one, so I think we'll go ahead and write it in. So I have 2t times pi over 4, or 2 times pi over 4, so this will be pi halves. And then I have the sine, and I have 4 times pi over 4, so this will be sine pi. And then plus 2 cosine, same thing, pi halves, and then cosine pi. And this is all over the negative sine cubed of pi halves. Do you see some zeros and some ones? Tell me what you see. What's sine of pi halves? That's 1. So this one's a 1. What's the sine of pi? That one's 0. So the whole first piece is now 0. What's the cosine of pi halves? 0. And what's the cosine of pi? 1. So the entire numerator is 0. And as long as the denominator is not, then the answer will be 0, right? And what is the denominator? Yeah, it's negative 1. So this is a 1, right? The sine of pi halves is 1. I've got it 1 cubed, and then I've got the negative 1. So there's a negative out here at the beginning that will move down. So this is actually 0 over 1. It's just 0. 0 over negative 1, so it's 0. What does a second derivative of 0 mean? Do you remember? It could be a straight line. That's a possibility. There's another thing it could be. It could be, depending on the curve. It could be a max or a min, depending on the curve. Typically speaking, it means that we should consider that there might be a change in concavity, right? It might go from concave up to concave down. It doesn't have to, right? Consider like x to the 4th. It would have a derivative that did that too, and it would have a peak or a valley, depending on the exact equation of it, like Annika said. But oftentimes there's a change in concavity. This is a very interesting graph, so we're going to graph it just because I think you should see it. So take your calculator and go ahead and put in the x and the y that it gave us. And we'll go from, I think 0 to pi is enough because my cosine 2 pi will complete the rotation. So we'll do cosine of 2t and then sine of 4t. And your window going from 0 to pi is sufficient. If you put pi over 2, or 2 pi, excuse me, it wouldn't hurt anything. Your t-step, I'm going to just leave mine at 0.1 unless it starts to be really too slow. I might change it. And I think negative 5 to 5, like I did in the last one, is probably sufficient.
That is a fun graph.
Isn't that a fun graph? It's like a bow tie, right? Bow tie. So we have a graph, just for the sake of you looking back at it later, perhaps it looks like this. I wasn't watching very carefully on how it drew, so let me do that real quick so we can put our arrows on the right direction. All right, so the arrows go like this, and then they come back around. That's what the graph looks like. Where would pi over 4 be? Well, you're welcome to actually change your window so that it actually stops at pi over 4, so you can have a better perspective of where pi over 4 actually lands you. And where does it look like it lands you? Where does it end? Can you tell? Another option, if you'd like, is you could make your window still go from 0 to pi and then go into your table and put in pi over 4. Although my table is struggling to give me values. I don't know what it's doing, but it's not doing it right. Anybody else's table working on that when you put in pi over 4? Does you? It does for x and for y? It should, which means you're where, Annika? The origin, yeah. So at pi over 4, we're back at the origin. And do you see how that looks like that kind of a straight piece? First of all, like we said, it could be, right? And you can also see how it could be a changing concavity piece. This piece is concave down and this piece is concave up, right? So we have those possibilities going on. All right. Another piece of calculus that we do when we're working with derivatives is we often find or are asked to find equations of tangent lines. So we're going to take a look at that idea. So we're going to find, this is example number 3, find an equation of a tangent line. At the given point. And our equation pair is x equals t to the 4th plus 2 and y equals t cubed plus t. So, and it gives us the ordered pair or the point 2, 0. Okay. Finding equations of tangent lines means finding slopes and putting it into a y equals mx plus b or y minus y1 equals m times x minus x1 equation, right? That's Calc 1 stuff. We're doing it in my Calc 1 class right now, in fact. So let's find the derivatives of each of the parametric equations. So what's the derivative of x? 4t cubed. And what's the derivative of y? Okay, everybody's good with that, right? Okay, but what I need to do is I need to create dy dx. That's not a problem. We learned how to do that. Dy dx is going to be 3t squared plus 1 over 4t cubed. But I'm supposed to be evaluating this at the ordered pair in the xy ordered pair plane, right, the Cartesian plane of 2, 0. What's the problem? I don't know x and y. And what I really need is I really need t. Could I find t if I know x and y? I should be able to, right? So you can take either of them. It has to satisfy both equations at once. So you want to make sure that you find the right t value. If we use the x equation, it will guarantee us to find only one t value. If we use the y equation, we might find more than one t value and then have to still use the x equation to make it work. So using x's equation is probably the most helpful. So x is t to the 4th plus 2. And if x is equal to 2, can you tell what t should equal? Yeah, t is 0. And if t is equal to 0, does that give you the right y value? That is, y is equal to 0 as well. It does. So this is actually my t value that I'm trying to evaluate it at. What happens?
It goes undefined.
It goes undefined. The denominator is 0. Okay, so this gives me an undefined slope. So think back, this is maybe a year or more. Undefined slopes. What does an undefined slope look like? Right, it's a vertical line. Okay, we're making progress. It's a vertical line. It's a vertical line. What does the equation of a vertical line look like? X equals. And what does x equal? 2. So this is my tangent line. It's x equal to 2. Now, that's clearly an unusual case. You're usually going to get a number out of that, and it's going to be the slope that you'd wanted, and that's fine. And you'd be plugging the numbers in and so forth. But this one ends up being a vertical line. But that's okay. We can have a vertical line. Okay, let me show you what happens when you don't get 0 in the denominator. So we're going to use the exact same pieces. We're just going to change the ordered pair point that we're looking at, okay? So instead of doing this, this is sort of like part A up here. Same thing on part B, except that we're going to change the ordered pair to be at 3, -2. Okay? So at 3, -2, what happens? Well, the first thing we need to find is t. So we can do the same thing we did last time. We can set the 3 equal to the t to the 4th plus 2. If we do, we find out that t to the 4th is equal to 1, which means that t could be what? Positive or negative 1. It could. And so we have to figure out which of those two values gives us the corresponding y value that we're supposed to be getting this time. Okay? So we have to be a little bit careful. Our y value that we're supposed to be getting is supposed to be negative 2. And our y equation is t cubed plus t. So you can try t equal to 1, and you can try t equal to negative 1. Which of the two gives you t equal to negative 2? Yeah. T equal to negative 1 will work. So when t is equal to negative 1, whoops, we get negative 2, so that is the value I want. I want t equal to negative 1. So my same dy dx I had above, dy dx is 3t squared plus t over 4t cubed. And I'm evaluating this at t equal to negative 1. Whoops. Negative 1. So if I put negative 1 into the numerator, what do I get?
4.
I get 4. Of the whole thing? What do you... I don't think I get 4. Did we get 2?
Yeah.
Okay. So I'd get a 3 from the beginning. I'd get a negative 1 from the end. So I think I have a 2. How about the denominator? That'd be a negative 4. So my slope will give, this is slope I'm finding, right? My slope is actually negative 1/2. So I have a slope of negative 1/2, and I have an ordered pair of 3, negative 2. So why, something wrong? What did I mess up on?
You're saying 3t squared plus t when it's 3t
I
squared.
put 1. There you go. The t was on the original equation. So is that my 3 that I needed? Or 4, was it 4 that you had? Yeah, it is. There we go. Thank you. Zooming in and zooming out. Lose my stuff. Negative 1? Okay. Alrighty then. Let's see. Y minus the y value. So the y value is negative 2, so this is y plus 2. Equals my slope, that's negative 1, times x minus the x value, which is 3. And we'll do some simplification. I have negative 1 or negative x. Let's see, plus 3 minus 2, so plus 1. Does that look okay? So that'll be the equation of our tangent. Any questions on that? Okay. Another type of calculus concept that we often think about, in fact, we've already encountered one of these by maybe just the sheer way that I created the examples, is horizontal and vertical tangent lines. We've created a vertical tangent line previously, at least we found one when we were looking for it. But sometimes we're actually asked to find places where it happens to. So that's the next problem that we're looking at. We're going to find all points, if any, of horizontal or vertical tangency. So we already talked about vertical tangent lines. When do vertical tangent lines happen?
Undefined.
Yeah, it's when the slope is undefined. And when do horizontal tangent lines happen?
0. So
Yeah, the slope is 0. That's what we focus on the most in Calc 1, is the slope being 0. And we're going to look at the equations x equals t squared minus 1 and y equals t to the 4th minus 4t. All right, so what's the derivative of x? 2t. And what's the derivative of y? Okay, and so in order to create horizontal or vertical tangent lines, it means that I either have zeros in the numerator, that creates a horizontal tangent line, or zeros in the denominator, that creates a vertical tangent line, but they can't be in both, right? So what I'm really trying to create, I mean, I can write this down if you wish, the dy dx, is I'm really trying to take the individual y prime and x prime that I just did and figure out where each of those individually are 0. So I need, let's see, what do I have? 4t cubed minus 4 over 2t. I need to figure out where this is equal to 0 and where this is equal to 0. Does that make sense? So that's our goal. I'm going to just shift this over to the side, and we're going to keep working with my x prime and y prime that I had. So when does the x prime, which is 2t, equal 0? When does that happen?
0.
Yeah, at t equal to 0. And when does y prime, which is 4t cubed minus 4, equal 0? That's a harder question. It happens at 1, and you might look at that and just, I mean, you can see that it's for sure at 1, but you might think to yourself, no, wait a minute, isn't that like a perfect cube thing? It is. Perfect cubes do factor very nicely. Difference of cubes, difference of squares. I didn't say that. None of that's what I just said, right? Let's try again. It's a difference of cubes is what it is, and a difference of cubes factors very nicely. I can take the 4 out. I would have t minus 1, and then I'd have t squared plus t plus 1. But anytime I have a difference of cubes, this piece doesn't equal 0 in the real number system. It equals 0 in the complex number system. So it doesn't give me any valuable information in terms of calculus because it doesn't work in the real number system. So it is in fact true, just like you guys said, that this is happening at t equal to 1, and that's the only place that it does. So when we're looking at horizontal tangent lines, that's happening when y prime of t equals to 0. So that's at t equal to 1. And going back to the original equation, when t is equal to 1, what is x? Actually, we'll just do it here. X of 1 is 0. How about y of 1? It's negative 3. So this is happening at 0, negative 3. And if we do vertical tangent lines, we're doing the same thing, but with the other equation. So the vertical tangent line is when x prime of t is equal to 0, which we said was at t equal to 0. So x of 0 is what? Negative 1. And y of 0 is what? Is 0. So again, this is happening then at the ordered pair negative 1, 0. Okay, so when we come back next time, I have one more example related to derivatives, and then what do you think we're going to do after that? Something that involves antiderivatives, right? The other half of calculus that we haven't talked about.